Hey guys, have you ever wondered if temperature has an effect on gas mileage? In this video, we're going to take a quick look and run some back of the envelope calculations to see if it does have a noticeable effect. So for the purpose of this video, I chose a Chrysler 200 with a 3.6 liter engine to be our hypothetical vehicle of choice. And I also changed up the format a bit. That would involve less writing, so I can do a bit more talking and maybe speed things up a bit. So for the purpose of this problem, we're going to assume that this car right here is traveling along the road at 80 miles per hour or 128.74 kilometers per hour with a constant velocity across level terrain under standard atmospheric pressure and with no wind and low moisture content in the air. Now, if we use these assumptions, we can assume that the car is in a static state, as in it's not changing its velocity or anything like that, which is unrealistic, hypothetically speaking, because cars are all undergoing minute changes in acceleration and velocity. But for the purpose of this case, we'll get close enough by just assuming that it has constant velocity, which means we can use a static equilibrium analysis to determine what the energy requirements are for this car. So the first thing you want to do, or the first thing that I did, was draw a Freebody diagram to try and tabulate all the forces that are at play on this car when it's driving along at a constant speed of 80 miles per hour. So here we have the free body diagram where we have our force of acceleration, which although the car isn't accelerating, it also has to exert a constant force to balance out the frictional forces here and here, and the drag force to prevent it from basically decelerating or slowing down. I guess decelerating really isn't a word that should be used, because acceleration can describe both positive and negative changes in rate. But I digress. The point is that this comes out to be a simplified free body diagram of what's actually going on with the car. And so to begin the analysis, I had to look up some Chrysler 200 specs. So we have coefficient of drag, we have weight, we have area, frontal area that is, and then we have weight distribution, which all play a part in determining what our variable balance ends up being. So using that information coupled with some of these relationships here to determine what our forces actually are, and I guess I'll go quickly through these relationships. For the force of drag, we have coefficient of drag times air density times velocity squared times frontal area divided by 2. For force of rolling friction, we have the coefficient of rolling friction times the normal force, NR for rear. These two correspond. For the coefficient of rolling friction, I got this equation from Engineering Toolbox, which is supposed to be good for basically cars with reasonably decent tires driving on concrete or asphalt. And so we have pressure in bar here, and we have velocity in kilometers per hour there. And then for the force exerted by the weight, we just have the mass of the car times gravitational acceleration. For this analysis, we're going to look at the temperature differential that you would see in some of the northern United States. So during the winter, we'd have temperatures of 0 degrees Celsius, or basically 32 degrees Fahrenheit on average, which gives us an air density of 1.2922 kilograms per meter cubed. And then during summer, we have a air temperature of 30 degrees Celsius or 86 degrees Fahrenheit, which gives us an air density of 1.1644 kilograms per meter cubed. And then some additional data that I used was basically conversion from bar to PSI, and then kilometers per hour to miles per hour. So once again, to go over my assumptions, we're assuming that we have a speed at 80 miles per hour or 128.74 kilometers per hour a constant velocity, level terrain, 1 atmosphere of air pressure, no wind, and dry air. Once again, we can use static analysis to find the force of acceleration to keep the system in equilibrium since we're assuming constant velocity. So starting with our math equilibrium equations, we can calculate in the y direction first, since we know most of those variables starting off. We have normal force and gravity are the only forces acting in this direction. So we have summation of forces in the y direction is equal to 0, which is equal to negative w plus normal force r plus normal force f, normal force rear and normal force front, which all has to be equal to 0 for this to remain in static equilibrium. So we're just going to sum our normal force rear and normal force front into normal force total to make this a little easier. And then we get our weight plus our normal force total, which we can solve for weight from by adding the weight to the other side. And then since we know what our weight is, which is equal to the mass times the gravity, which comes out to being 15,911.82 newtons, or 15.911 kilonewtons, which is then equal to our normal force total. So now that we have a normal force total for the car, we can break it up into its components based on the weight distribution that we had. So since the Chrysler 200 has a 40% rear, 60% front weight distribution, we can get a normal rear force of 6.3647 kilonewtons and a normal front force of 9.54709 kilonewtons. And then we can use that equation for rolling friction coefficient. And if we plug in and convert our 40 psi air-to-air pressure to 2.7586 bar and use our 128.74 kilometers per hour or 80 miles per hour speed, we get a coefficient of rolling friction of about 0.01433, which is close to 0.015, which is what you expect from a car who is rolling across concrete. So once we have that, we can move on to solving for our friction force front and friction force rear. So we can take our coefficient of rolling friction and multiply that times the normal force rear and the coefficient of rolling friction times the normal force front to give us our 0.912 kilonewtons and our 0.136 kilonewtons of frictional forces. And so now that we have those, we've basically taken care of all the forces that are acting along the y direction. So we can take care of the forces that are acting along the x direction. So that would be acceleration and drag. So forces in the x direction are going to sum up and be equal to force of acceleration minus force of drag minus frictional forces together is equal to 0. So we can move everything to the other side or add it to the other side to cancel these out. And we get our force of acceleration is equal to force of drag plus our two frictional forces, which we can sub in our force of drag equation and get our coefficient of drag times our air density times our velocity squared times our area divided by 2 plus our frictional forces. And once we have that expression, we can begin putting in our variables. So for this equation, we can sum up our two friction forces that we had earlier to get 228.015 newtons. And then we can plug in our variables for our winter temperature, which is our 1.2922 kilograms per meter cubed air density, and our coefficient of drag, which is 0.34, and our speed, which we have to convert to meters per second to keep our units the same. If you go through this, all of our units end up crossing off to leave us with this expression here, which then comes out to being force of acceleration is equal to 767.28 newtons plus 228.015 newtons, which gives us our force of acceleration at 0 degrees Celsius being 995.304 newtons for a Chrysler 200 under basically perfectly ideal conditions traveling at 80 miles per hour. If we repeat this for 30 degrees Celsius, the only thing that changes is our air density. Although realistically, a lot of other factors would probably change too as a result of the higher temperature, like our tires and how they respond to the road. But to not get off task, that all sums out to about 919.42 newtons. But taking that information, we can use our force at 0 degrees Celsius and our force at 30 degrees Celsius and determine the percentage difference, which comes out to be 7.624%. That's 7.624% less force to drive at 80 miles per hour in 30 degrees Celsius air than at 0 degrees Celsius air. So now to actually convert this into like gas mileage, you would have to essentially calculate the energy density of gas as well as the efficiency of the engine and a whole bunch of other fun stuff that would draw this video out to probably like an hour long. So the short and easy of it is basically that if you got 24 miles per gallon during the winter, you would get 25.8 miles per gallon during the summer. And so obviously the better gas mileage your car gets, the better your conversion ratio is. So for example, if you had a car that got 30 mpg during the winter, you'd be looking at like 32 point something during the summer. Now this isn't a significant difference, but it's actually a sizable amount because if you have the opportunity to increase something by 5% efficiency, over the course of the vehicle life, that's quite a bit of difference in cost of gas. So I guess the moral of the story is, if you can choose between driving in the winter and driving in the summer, it probably pays to drive in the summer. So thank you for watching, and hopefully you enjoyed this video. This is Example Problems, signing off.